All right. So on the next page, what we need to do is determine whether the sequences converge or diverge. All right. If they converge, then give its limit. So basically what we're trying to do is determine the limit as n approaches infinity for each one of these. Right? Because if we're dealing with a set of positive integers, yeah, I suppose it could converge onto a particular value after like n equals 10. But if it's a function, if it's related to some known function, then it's probably going to ease its way into its limit. All right. It's not like a piecewise function where part of it could just be y equals 10. So that's your limit. That might happen very early on. All right? You don't even have to get out to infinity in order to see that. These are different. These are more complicated. Some of them are not bad though. Like number one, that's straight up L'Hopital's rule. All right? Because if I were to find the limit as n approaches infinity of n plus 4 over 3n minus 2, just by plugging and chugging away, I'd get infinity over infinity. All right? Infinity over infinity or 0 over 0 is never a final answer. All right? It's an avenue. It's an approach. It's telling you that you can get a limit, you just have to do the work. All right? Here it's telling us that L'Hopital's rule applies. So once you make that determination, well, apply the rule by taking the derivative top and bottom separately from one another. So with respect to n, derivative of n plus 4 would be 1. Derivative of 3n minus 2 would be 3. Limit of a constant is equal to a constant. All right, so it converges. Right, it converges, and it also asks us to give the limit if it did converge. So it I think I might have missed because I don't have guts all over my hand. It looked like it had kind of like a hard shell, and I also didn't feel like that satisfying crunch. Yeah. All right. Well, anyway. Number 2, limit as n approaches infinity of n squared over e to the 4n. Well, if I plug in infinities, again, plugging and chugging away, I'm going to get infinity squared, which is infinity, and e to the infinitieth power, which is infinity. So L'Hopital's rule applies again. So derivative top and bottom, I'm looking at 2n over 4e to the 4n. All right, derivative exponential function, keep it as is and then multiply by the derivative of the exponent, which would be 4. All right, again, derivatives of the top and bottom separately, not quotient rule. All right. So, good news, bad news. Bad news is, if I plug in infinity at this point, I still get infinity over infinity. The good news is, I can do something with that. It means L'Hopital's rule applies. Again. So, derivative top and bottom. 2 over 16 e to the 4n.
So you just keep on rolling until you can.
Until you get something that is finite. All right. So in this case, if I apply the limit, I'm going to get 2 on top, so that's not infinity. So one way or another, I'm at the end of this journey. On the bottom, if I plug in infinity, I'm getting e to the infinitieth times 16, which is infinity. So then the only thing I would need to know is what 2 divided by infinity is. or what 2 divided by infinity approaches, because again, infinity is not a place, so you can't actually divide by it because it's not a number. But if I continuously increase the denominator of a fraction, what happens to the overall value of the fraction? What is it going to? 0. So it converges. Yeah, because if I start off with, like, let's say 2 over 10, that's equivalent to 1/5. 2 over 100, 1/50. All right, 2 over 1,000, 1/500. The fraction's getting smaller and smaller and smaller. All right, eventually till it gets to 0, if it could. All right, so L'Hopital's rule twice. So the next one must be L'Hopital's rule 3 times.
You did a chain rule? You did L'Hopital's rule for the denominator?
For the denominator chain rule, yeah. All right, so, yeah, I was just kidding. Number 3 is not L'Hopital's rule 3 times, because what you're dealing with here is the idea that you can't settle in on a particular number for the limit of the top as n approaches infinity. If I put cosine of infinity, it's like, okay, well, I don't know what it is. I know it's somewhere between -1 and 1, but I don't know where it is. So it would be one of those indeterminate situations, but not the word indeterminate, more like can't be determined. All right, so another approach is required. In this case, we use what's known as the sandwich theorem, or to make it sound less stupid, we call it the squeeze theorem, which only barely sounds less stupid. All right, so what I need to do here is figure out what 2 functions this one would be sandwiched or squeezed in between. And you're like, well, if I could do that, this would be a whole lot easier. Well, what you do, trig functions are a lot easier to handle when it comes to the squeeze theorem, because sine and cosine functions always exist, regardless of what is contained within the function. They always exist between 2 values. Two very specific values. The cosine and sine functions, I mean, if you were to graph a sine function, you put whatever you want inside of it. All right, cosine of pi x minus 3/8. It doesn't matter what you put inside. Pi x squared minus 3/8. It's always going to bounce back and forth between -1 and 1. All right, and that has to do with the amplitude of the function. Right? If this were 2 times the cosine of 5n squared, then it would bounce between -2 and 2. But a sine function, cosine function always bounce between -1 and 1. And then you might say, well, what about a tangent function, secant function, blah, blah, blah. And I would say, well, no, because those are infinite. Right? They go the other way. The only 2 functions out of the 6 trig functions that are finite in their range are the sine and cosine functions. Everything else is infinite in some capacity. All right? So I have this relationship. I can rely on this. But what I need is the limit as this approaches infinity. So what I'm going to do is I'm going to build this fraction from this inequality. You can multiply, divide, take a radical, whatever you want to do to an inequality, as long as you do it to each part of that inequality. All right? So what I want to do is divide each part by the square root of n. Okay, so now what I want to do is find the limit of each part of this inequality as n approaches infinity, which is more writing than you want to do, but it's got to be done. Limit as n approaches infinity of -1 over root n is less than or equal to the limit as n approaches infinity of that, cosine 5n squared over root n, is less than or equal to the limit as n approaches infinity of 1 over root n. All right, now I haven't been using my calculator just because I'm showing you these skills, which are important, but you know, if you're in a jam, go to the calculator. All right, but this is along the same lines as the previous one, where if I were to substitute in the infinity for n, I'd be looking at -1 over the square root of infinity and +1 over the square root of infinity. In each case, I get a result of what? 0. All right, so the outer functions have a limit that's equal to 0, both of them. We know that the inner function is squeezed in between those two outer functions. So whatever the limit is of the two outer functions, the inner function has to take on that same limit. All right, it can't escape from those boundaries. All right, so it's been squeezed within. So they came to 0 at infinity. So from the both ends, they came to 0. And then you have that inner function that's living in between. So it's literally being squeezed in between those two functions. And so once they get to a point where they're indistinguishable from one another, that third function must take on all the characteristics of the two outer functions, all right, including its limit. So my final answer here would be that the limit as n approaches infinity of the cosine of 5n squared over the root of n is going to be equal to 0, and that suggests that this is converging. And honestly, this is like the best example for converging because it's converging in that the limit exists, but it's also like fitting what a person would think of when they think of the word converging. There are two things coming together.
Would it always be from -1 to 1, or would it vary?
For cosines and sines, always -1 to 1. So actually, if you're looking at number 6, which I won't do now, I'll star that one, but that's also a squeeze theorem problem. You would start this one off by saying that the sine of 3 over n squared is between -1 to 1, and then multiply everything by n squared, and then apply the limit. I'll put a star on that bad boy. All right, numbers. You know what? I'll put a star on 4, 5, and 6. 5 is very scary looking, but it's not hard at all. Oh, you know what? If I'm going to do that, I'm just going to put stars on everything else. Because numbers 8 and 9 refer to the rules that we talked about on the previous page, r to the nth. If the absolute value of r is less than 1, then it converges. If it's greater than 1, it diverges. So like you can use that information to help you with 8 and 9. And this is a constant, so that's like nice. And so when I first started playing that, I was like behind the curve, and now I'm like a rock star. Yeah, it's great. I appreciate that. I'll show you my village one day. I'll send out a picture on Remind. So it's pretty solid. Check that beast out. I almost said a bad word. All right. So while you're admiring my village, take a look at number 5 here. So, just a refresher on the directions. Said determine whether the following sequences converge or diverge. And basically what we're talking about is whether or not the limit exists. All right. So now the thing that I always found to be confusing when I was a student is the transition between a sequence and a series. All right. Because some of the things that are true for a sequence will no longer be true for a series. All right. And we'll get to that in a little while. But here, all we're looking to show, in order to show convergence for a sequence, this is what you got to drill into your heads. For a sequence only is whether the limit exists, all right? So as n approaches infinity. So it's kind of like what we were doing before. Limit as n approaches infinity, except we don't have to integrate. So that's good news. I just have to find the limit of this. Now, this would be a beast to put in your calculator, but not impossible. If you're in doubt, put it in your calculator, see what's going on. All right. It will exist for large values of n, so that's good news. All right. But what I want to do is I want to clean it up a little bit. All right. Because I know that the limit of a product is equal to the product of the limits. So limit as n approaches infinity of e to the negative 3n squared multiplied by the limit as n approaches infinity of the inverse tangent of the square root of 7n over n squared minus 9. All right. Now, focusing on this one, you could actually figure it out. I mean, you can go through the process. It's not terrible, but it would be a complete waste of time. So, like you can get this result. It would be doable. But let's focus on the other guy. This is the same as 1 over e to the 3n squared. I'm going to ignore the one on the right, the factor on the right. I'm just going to call that some limit L.
Why is it 3n squared, not 3?
3 and, oh, I don't know. I corrected it into still the wrong answer. Oh, you know what? Let me see. Come on. I erased it and then I wrote it again as a 2. It's not good. All right. Well, anyway. So what is the limit as n approaches infinity of 1 over e to the 3n to the 5th? Yeah, it's going to be 0. All right. So we're looking at 0 times L, which is 0.
Why is it 0?
Because this is going to be 1 divided by something extremely huge. Right? So if you were to take 1 and divide it by like 100,000, it would be very close to 0. If you divide it by something even larger, it's going to get even closer to 0. So as you get closer and closer to infinity for n, the value of the ratio is going to get closer and closer to 0. What is that? What?
What is L?
L is just some limit. But basically, all I'm saying here is, since this turned out to be 0, didn't matter what this was going to be. So I didn't even bother figuring it out. I just put a placeholder of L in there. All right. All right, so little strategies. Let's see. Oh, number 6. We'll do that one too. Because this was the the squeeze theorem situation. So we know sine and cosine functions always exist between -1 and 1. So I know that this statement is true. All right. All right. So what I need to do is find the limit as this bad boy approaches infinity. But I want to build my inner expression into equaling that. All right. What I want to do is tailor this so that I have a function that I know is sandwiched or squeezed in between two other functions. So that if I could find the limit of the two outer functions, if they're the same, then the inner function must take on the same limit. All right. So I'm going to multiply by n squared, and that's going to give me -n squared is less than or equal to n squared times the sine of 3/n squared, which is less than a positive n squared. All right. The next step in the process would be, because this is still a true statement, it's sandwiched in between. I want to find the limit of this as n approaches infinity. All right, so for the lower bound, I'm going to get infinity squared is infinity, negated is negative infinity. The upper bound will be positive infinity. And so this is not a case where it ended up squeezing anything. All right. So what you would want to do at this point is try a different technique. Okay? And that other technique would be to use a calculator, because I mentioned that L'Hopital's rule is a strategy, direct substitution is a strategy, the squeeze theorem is a strategy, but sometimes even before you get to that, the graphing calculator is your strategy. Right? So I'm just going to type in that original function using x's and see what it gives me for large values of x. If it gives me something that's inconclusive, then we would decide that the limit does not exist, or a contradiction anyway. Of course, it could give you a 3. Just make sure I'm in the right mode. Type it in correctly, good to go. All right, so what we're looking at is on the calculator, I'll just draw a quick sketch. All right. As it goes out to infinity, graphically it appears to be approaching 3. But numerically, if you use the table trick that I showed you, you will see that the limit is in fact equal to 3. All right, so L'Hopital's rule. The squeeze theorem was inconclusive. It would have been conclusive if these two bounds were exactly the same. Not conclusive, so we try something else. The other strategy that we go for is the calculator approach, and it's generally not going to let you down, right? So it's a good way to handle things. Let's see. Oh, yeah. Number 11. Look at that problem right there. Let's tackle that one. We're looking for the limit as n approaches infinity of 3 to the nth over n factorial. Oh, by the way, sorry. It converges. Gave us a finite value, so it converges. Got to answer the question that was being asked. Same for the other one. All right, so this one you might want to go directly to the calculator and see what's going on. All right, but I do want to take a minute and talk to you about that n factorial part of it. All right, because it's hit or miss as to whether or not you've seen that in any kind of detail before. And it's something that we're going to explore a great deal in this unit with the Taylor and Maclaurin series. All right, so n factorial is defined as n times n minus 1 factorial. All right, which is kind of a weird thing to think about. But what this is telling us is that you're multiplying by consecutively lower and lower values until you get down to 1. Right? So if I were to, for example, start off with 5 factorial, that would be the same as 5 times 4 factorial. Now that 4 factorial would be the same as 4 times 3 factorial. That 3 factorial would be the same as 3 times 2 factorial. And the 2 factorial would be the same as 2 times 1 factorial, but 1 factorial is just 1. All right. So this generalizes to, kind of a shorthand way of doing it. And this is the way that, if you've seen this before, this is the way you may have learned it, which is to just say, well, forget about all those steps. I'll just do 5 times 4 times 3 times 2 times 1. All right. And numerically, that ends up giving you a value, in this case 120, but that's not really what's important. All right. This general rule of thumb is really what gets us where we need to go. All right. So what we have to do here is kind of consider the situation. Again, it's a race between the numerator and the denominator. Whichever gets to infinity first is going to define what the overall limit is going to be equal to. Right? So whether you do that in your calculator or you do it by hand, either way you have to come up with some sort of rationale behind this. All right? So what I'll do is just come up with a couple of test cases here. Let n equal 1. If n were equal to 1, I'd be looking at a sub n would be equal to 3 over 1 factorial, which is the same as 3 over 1, or 3. All right. If n is equal to 2, a sub n would be 3 squared, so 9, over 2 factorial, which is going to give me a 4.5, because 2 factorial is equal to 2. 2 times 1. All right, so 9 over 2 is going to give me 4.5. All right, and all we're looking to do is see where this is going. Is it settling on a particular number, or is it going to increase without bound? So 3 to the third is 27. over 3 factorial. So 27 over 6. We're talking, what, 9 something or other. So 27 over 6. Oh, that's 4.5. Hold on a second. 2.25. I screwed up. Oh, wait, no, I didn't. Well, they're both 4.5? That's fun. Three to the 4th power is 81 over 4 factorial. So 81 over 24. All right, so it seems to be bouncing around a little bit here. So maybe you try the next value, but maybe you say, okay, let me skip a few. I'll try the next one and then I'll skip a few. 3 to the 5th. Oopsie daisies. 243 over $1.20. 2.025. And then skip a few and let me do n equals, can it handle 10? Yeah, I guess so. So that talking about 0.0163 approximately. All right, so if you were to continue on as n approaches infinity, it seems like the values are getting smaller. So it spiked up a little bit initially. All right, for 1 it gave us just a clean 3. But then it jumped to 4.5, and then after that it starts steadily working its way down. The suspicion being that a sub n is going to be approaching 0. All right, but maybe you're not convinced, at which point you go to your calculator and take a look. All right. Just because I don't know that everybody has seen this before, if I wanted to type something factorial in my calculator, n factorial, that factorial key is in the math menu. Math, scroll over the probability, or to probability, and select option 4. Math probability option 4. So type the number in first and then select math probability option 4. It'll bring up the number with an exclamation point after it, and then you can run the numbers. All right. So in this case, calculator-wise, I'll put the function in and then I'll display it. A little bit of glare now.